In this video, we're going to learn how to implement a stack data structure in C, as well as a library of associated functions for working with a stack. So let's go over an example of what a stack actually is. So a stack looks like this. Here we have the values 8, 7, 4, 9, and 2. We could call each one of these values an item in the stack. And together we could say the stack stores a collection of these items. And the stack would have a size 5 because there's 5 items in the stack. Now a stack is a last in, first out data structure. And it works kind of like a stack of papers stacked on top of one another. So with a stack of papers, we could put a paper down on the top of the stack, and we can pick a paper up from the top of the stack. A stack data structure works pretty much the same way. We have two main operations. We can pop a value off the top of the stack, and we can push a value onto the top of the stack. So for example, with this stack here, after doing a pop operation, we would pop off the value 8 because that was the top of the stack. The stack size would now be 4, and 7 would be on the top of the stack. If we did another pop, we would then have 4, 9, and 2. The item popped would be 7. The stack size would now be 3. Now we could also push values onto the stack. If we pushed 7 onto the stack, it would then look like this, with 7, 4, 9, and 2. And we would have a stack size of 4. We could then push on 5, and we would have 5, 7, 4, 9, and 2, with a stack size of 5. Now there's some other operations we could perform with a stack as well. We could check to see if a stack is empty, in other words, if it contains no items. We could check to see if a stack has reached a maximum capacity, because many implementations of a stack data structure have a certain max capacity. We could also implement a peek operation that returns the value at the top of the stack without popping it off. We could also create operations to create and destroy a stack. So let's go over how to implement a stack now in C. So our stack data structure is going to look like this. We'll say typedef struct and then stack. So we're using typedef to define a new type called stack. And it's going to be a struct with multiple members. Now there's different ways of implementing a stack using an underlying data structure. Some stacks are implemented with, for example, linked lists. We're going to use a dynamically allocated array to implement our stack. And we'll call that dynamically allocated array collection. So we'll say int star collection. So collection is going to be a pointer to a dynamically allocated array of integers. Now our stacks will also have a capacity and a size. So the capacity of the stack is going to be the size of the dynamically allocated array in terms of how many ints it can store. And the size of the stack is going to be the number of elements stored in that dynamically allocated array. And we'll use these members to help manage our stack. So our stack is going to store a collection of int values, but it could really be any type, including a struct. We'll include a couple C libraries to help us define the operations to work with stacks. So the first thing we'll do is include stdlib.h, because this library includes functions like malloc and free for working with dynamically allocated memory. We'll also include stdbool.h, so we can use the bool type. And our operations will look like this. We'll have a function for creating stacks. We'll say stack star create stack int capacity. So this function will return a pointer to a stack that's been dynamically allocated on the heap. And that stack is going to have this capacity. So its collection, dynamically allocated array, will be able to store this many items. Now it's very typical when working with data structures to create them on the heap, just because of the nature of what they do and how they work. So that's why we're creating the stack on the heap. It is possible to create data structures on the stack, which is not the same stack we're talking about here. The stack in that case is a different portion of memory. But we're going to use stacks on the heap because that's what's more typical with working with data structures. We'll also create a function to destroy the stack. So we'll say void destroy stack, stack star stack. So this function will accept a pointer to the stack, and it's going to free the dynamically allocated memory associated with the stack. We'll make functions for determining if a stack is full or empty. So bool is full, stack star stack is going to return true if the stack is full and false otherwise. Bool is empty, stack star stack is going to return true if the stack is empty and false otherwise. And next, we'll declare our pop, push, and peek functions. So we'll say bool pop stack star stack int star item. So pop is going to attempt to pop an item from the stack. It's going to return true if it successfully popped the item and false otherwise, because we can't pop an item from a stack that's empty. It's going to return the item via pass by pointer using this item parameter here. Next, we'll say bool push stack star stack int item. So push is going to push this item onto this stack, and it's going to return true if it was successful and false otherwise, because it's possible that the stack is already full, in which case we can't push this item onto the stack. And then finally, we'll say bool peek stack star stack int star item. And the peek function is going to return via pass by pointer the item at the top of the stack, but it's not going to pop it off the stack. It's still going to be on the stack itself. And again, this function will return true if the item was successfully peeked and false otherwise, because if the stack is empty, we can't really peek the item at the top of the stack. So let's actually implement these functions now. We'll implement create stack first. So we'll copy and paste this, and then down here, we're going to create our stacks. So the first thing we'll do is check to see that the capacity is greater than 0. If it's not, we can't really proceed, because we can't really create a stack that has 0 or less capacity. So if capacity is less than or equal to 0, we're going to return null, because we're not going to allow a stack with a negative capacity or a capacity of 0. Next, we'll use Malloc to dynamically allocate enough space to store a stack. So we'll say stack star stack is equal to Malloc size of stack. So Malloc is going to allocate enough space to store a stack, and it's going to return a memory address that we're going to store into stack here, and we use that to access our stack. Now if Malloc fails, it's going to return null. So we'll check to see if stack is equal to null. And if it is, we'll also return null in this function, because that's going to be a signal that this function failed as well. Next, we'll allocate enough space to store a collection with this capacity. So we'll say stack collection is equal to Malloc size of int times capacity. So here we're using Malloc to allocate enough space to store capacity number of int values. And again, Malloc is going to return a memory address that we're going to store into the collection member of our stack. And again, if Malloc failed, collection would be set to null. So we'll check for that. If stack collection is equal to null, then we're going to return null, because we're going to say that we failed to create the stack. We're also going to free the stack before we do that, because if we did get to here, it means that this dynamic memory allocation must have worked. And if that's the case, we want to free that memory. And then finally, we'll set the capacity and size of the stack. So we'll say stack capacity is equal to capacity, and stack size is equal to 0, because initially there's nothing in the stack. And then we'll return stack. will return the pointer to the stack that we've allocated on the heap. Next, we'll make a function to destroy stack. So we'll copy this. We'll paste it down here. And to destroy a stack, we'll say free stack collection and free stack. So first we'll free the dynamically allocated memory for the collection dynamically allocated array, and then we'll free the dynamically allocated memory for the stack itself. Our isFull function will look like this. We'll say bool isFull stack star stack, and we'll check to see if the stack is full using its size and capacity. So we'll say if the stack capacity is equal to the stack size, then the stack is full. So we'll do a check for equality here, just to see if the stack capacity is equal to the stack size. And we'll return whether that's true or false. Our isEmpty function will look like this. We'll say bool isEmpty stack star stack. And here again, we'll check the size. We'll say return whether or not the stack size is equal to 0 or not. So if the stack size is equal to 0, that means the stack is empty. So now we can probably test out some of these functions. We could create a stack, we could destroy a stack, and we could check to see if a stack is empty. So let's test out some of these functions. Here we'll say stack star stack is equal to create stack 5. So we'll try to create a stack with capacity 5. We'll make sure that the stack was actually correctly created first. We'll say if stack is equal to null, then output that we have an error. So printf error creating stack \n, and we'll return 1. We're going to return 1 instead of returning 0 because returning 1 is a signal to the shell, to the terminal, that something went wrong in the execution of our program. Next, we'll check to see if our stack is empty. And it should be empty right now because we've just created it. So here we'll say if isEmpty stack printf stack is empty \n. And then finally, we'll destroy the stack. We'll say destroy stack stack. So we'll save and run this, and we should get back stack is empty. And we do. We get stack is empty there. What if we tried this though? What if we tried to create a stack with capacity 0, which doesn't really make any sense? If we save and run this, we now get error creating stack, and the program exited with code 1. So we're handling that case okay. We'll flip this back to 5 though, to make a stack that can store 5 items. Next, we'll implement a push function that's going to push items onto the top of the stack. So we'll copy and paste this, and then down here, we'll define our push function. So we'll paste it here, and the push function is going to push this item onto the top of the stack, if it can. It can't push the item onto the top of the stack if the stack is full. And we now have a function to check for that. So if isFull stack returns true, we're going to have this function return false because it will have been unsuccessful in pushing this item onto the top of the stack. Otherwise, the function is going to return true. And what we'll do is push this item onto the top of the stack. And we'll do that by setting stack collection at the index stack size to the item. So we're setting the element in the collection array at the stack size index to item, to put the item at the top of the stack. Now, because we've just put an item onto the stack, we're going to have to increase the stack size to reflect that. So we'll also say stack size ++. So that way, the next time we go to put an item onto the stack, it'll put it at the next index in the array. So the first index in the collection array becomes the bottom of our stack, and we stack elements on top of it, one after the other, by setting each subsequent array index. Let's try pushing some items onto the stack. So here we'll say push stack and then 2. And after doing this, the stack size should now be 1. So we'll say here printf stack size %d \n, and we'll put the stack size here. And we'll save and run this. And now we get a stack size of 1. Let's try pushing some more items onto the stack. We'll say push stack 9, push stack 4, push stack 7, and then push stack 8. To push 5 items onto the stack. Now, because our stack has a capacity of 5, at this point it should be full. So let's check that. We'll output the stack size again, and we'll also output whether the stack is full. So if is full stack printf stack is full \n. So we'll save and run this. And now we get stack is full, and we have a stack size of 5. Next, let's try pushing an item onto the stack when we know it's already full. So here we'll say bool try push is equal to push stack 5. So this time we're going to store the return value of push because we know it's going to be false. We know that we are not going to be able to successfully push 5 onto the stack because the stack is already full. And we'll say here if try push is equal to false, printf push failed \n. And we save and run this, and we get here push failed. Next, we'll implement the peek operation to peek at the value at the top of the stack without popping it off the stack. So we'll copy and paste this, and we'll provide a definition down here. And the peek function will look like this. We're going to check to see if the stack is empty. Because if the stack is empty, we can't really peek at the value at the top of the stack because there's nothing there. So if isEmpty stack is true, we're going to return false. Otherwise, we'll return true. Now to peek at the value, we're going to access the value in the collection dynamically allocated array at stack size -1, because that's the current top of the stack in terms of where the values are stored in the array. And we're going to return this value using pass by pointer. So we're going to dereference the item pointer, and we'll store this value into that location in memory. So we'll call this function using a memory address of an integer. And by dereferencing that pointer, by dereferencing that memory address, we can store the value at the top of our stack in there. Let's try out the peek function. So in main here now, we'll say int peek val is equal to 0, and we'll call peek. We'll say peek stack, and we'll give it the memory address of peek val. And then we'll use printf to output peek val. So printf peek val %d \n, and we'll output peek val. And if we save and run this, we get a peek val of 8. And that makes sense, because the last thing that we successfully pushed onto the top of the stack was 8. Finally, let's implement the pop function. So we'll copy and paste this, and we'll define the function down here. And pop will look a little bit like peek. So with pop, we'll say if isEmpty stack return false, because we can't pop an item off the stack if there are no items on the stack. We'll return true if we can successfully pop an item from the stack. So to pop the item, we'll again say star item is equal to stack collection at stack size, but this time instead of -1, we'll actually decrement the stack size first. So we'll say stack size minus minus. So the reason we're doing this is because the pop function actually modifies the top of the stack. By decrementing size, we're modifying where the top of the stack is actually located. We can keep the old value in the collection array. That's not going to make a difference. What's going to matter is where we consider the top of the stack to be, because that's where we're going to be popping items from. That's where we're going to be pushing items onto. So we don't actually have to do any deletion of data. We can just decrement the size. And by doing that, we're modifying where the top of the stack is. And then again here, we're dereferencing item to return via pass by pointer the actual value of the item at the top of the stack. Next, we can try out our pop function in main. So we'll make a loop here to actually pop the items from the stack. We'll say int pop val is equal to 0. And we know we have 5 items on our stack. So we'll make a loop that's going to iterate and run 5 times. We'll say for int I is equal to 0, I is less than 5, I plus plus. And we'll pop each item from the stack. We'll say pop stack and pop val. And we'll printf the popped value. So we'll say printf popped value %d\n, and we'll output pop val here. And if we save and run this, we get pop value 8, 7, 4, 9, and 2. And you can see that the values were popped off in the exact opposite order that they were pushed on, with 2 being the last value popped off, when 2 was the first value we pushed onto the stack. So the stack does appear to be functioning correctly. Let's see what happens if we try to pop an item from the stack when the stack is empty. So here we'll say bool try pop is equal to pop stack and pop val. And if try pop is equal to false, we'll printf that pop failed. And it should fail, because at this point we know that our stack is empty. So we'll save this, run it, and we get pop failed in that case. It'll be the same thing if we try peek. So here if we said bool try peek is equal to peek stack, and we'll say peek val here. If try peek is equal to false, we could printf peek failed, because we can't peek out a value on a stack if the stack is empty. So we'll save this and we'll run it, and we expect to get peek failed. And we do. So this is how we can create a stack data structure in C, as well as a library of associated functions for working with those stacks. Check out portfoliocourses.com, where we'll help you build a portfolio that will impress employers, including courses to help you develop C programming projects.